And without any further ado, I will invite your main presenter today, your main speaker, Peter Thompson, to share his screen and kick off the call. Thank you so much. Over to you, Peter.
Okay, hello everybody. Hopefully you can now see. So this is our second webinar.
I can't see the screen share at the moment, Peter.
Oh, maybe I need to do that again. Showing paused. Show. No, I don't want to do that. I want to do that. Is that better?
No, not at the moment. I'll let you know as soon as I can see it. I may need to click the play button to start sharing. Let me take control of the screen share, then I'll send it back to you. Bear with me a moment. And then let me send it back to you, Peter. There we go. So please try taking over that now. Okay, there we go. I can see your whole screen share at the moment. So just select it onto perfect. Thank you so much.
Right, okay. Is that working now?
Yep, that's working perfectly. Hello, Peter. I've lost your sound. I can see your screen now, but I can't hear you. Hello, Peter. Are you there? Ladies and gentlemen, sorry for this little interruption here. We seem to have lost Peter's sound at the moment. I wonder if I could invite Neil or Lucy to come in and take over.
Right, well, one moment. I will just start up the presentation myself off my desktop and share it. If you've passed the token to me, I will share it. Of course, I didn't practice it, so this will be a right. It's on show.
Okay.
Can I now become the presenter?
Yeah, I will hand it over to you now, Neil. There we go. Peter, if you do get it reconnected at some point, please do just come on mic and let us know, and we'll hand back over to you.
Right. Sorry about that. I had some Wi-Fi problems.
Ah, we've got you back now, Peter. We've got you. We can hear you.
Right. Okay. Sorry, I had some Wi-Fi problems just then. Right. Okay. As we were.
The presenter.
Right, so
there we go.
Take Peter back.
Great. I can see that now. So we're at the recap section. Right. Sorry for our interruption, ladies and gentlemen. So we're all good to go now. Over to you, Peter.
Okay. Right. If you have trouble seeing me or hearing me, then you know, stick something in the chat to let me know. Okay. So this is about the PEnDAR project. Just to remind you, our goals are to consider how to enable a validation and verification of cost and performance for distributed and hierarchical systems, and provide early visibility of cost and performance hazards. So hopefully avoiding costly failures and maximizing the chances of successful in-budget delivery of acceptable user outcomes. And the partners are ourselves, Predictable Network Solutions, Test and Verification Solutions, and Vodafone Group, and the project is supported by Innovate UK. So in particular, this focus group is an opportunity for us to explain some of what we've learned about how things work in this distributed network world, and to help to hopefully give you some insight into what's required in terms of sustainability and viability of applications in this context. And in return, we're hoping that you can help us find out in which markets or sectors or application domains with the benefits of using these kind of approaches outweigh the obvious costs. and which are the major benefits, and how could this methodology actually be consumed? Is it worth constructing tools, or should it be offered as a service, or what would work? So that's what we're hoping to achieve here. Okay, so what we've promised for this second webinar is to provide an outline of this. We've talked around it. We've said that lots of things can be done. Let's now get into the meat of this and actually support these assertions with a bit more detail about how this actually works. So I'll start with this little diagram we looked at last time. And remember, the core of this is the little sort of yellow hexagon in the middle, looking at the interaction between the delivery of outcomes and the consumption of resources, and that's the core of what we're going to look at today. But around that, we have issues of how to understand the impact of mitigating or propagating exceptions or failures, how various sorts of variability, either self-induced or externally created, impact on the system, and how the performance of the system depends on scale, both in time and in space. So that's the context we're working in. We'll come back to this later. So how do we do an analysis of this combination of resources and costs, resources and performance? So we start with a functional decomposition. We have our subsystem, and we take each subsystem in isolation, and we analyze the performance of that subsystem, modeling the whole of the rest of the system as a delta Q. I'll remind you what delta Qs are in a moment, but basically it's something where there's a distribution of delay and exceptions in terms of how that system responds. We quantify the resource consumption of our subsystem, which may be dependent. We look at the sharing of resources within the system, so quantifying the resource costs of the different subsystems, and indeed even between systems to quantify the opportunity cost which running this system represents against other systems using the same infrastructure. So that's where we look at the shared resources, and then we can do successive refinements of this, where we consider higher order couplings, and if necessary we can iterate the whole analysis till we get to a fixed point which encompasses all those couplings. Now, the combination of performance and resource consumption is something that we refer to as a quantitative timeliness agreement. So if you like, that's what's represented by the barrier of that green rectangle on the right there. That across that we impose a certain load, and from that we get a certain response, and that pairing of load and response is something we call a quantitative timeliness agreement, or QTA. Now, we've only got a limited amount of time today, so we're not going to have time to get into the questions of opportunity costs, of couplings or fixed point iterations, but hopefully we can give you enough of a flavor that it will be at least conceivable how those things could be worked through. Okay, so let me say a little bit more about delta Q, just to make it clear what we mean here. So delta Q is a measure of the quality impairment of an outcome. Ideally, we would like things to occur instantaneously and without any failure. Nothing in the real world is perfect, so there always is some quality impairment, so delta Q always exists. And delta Q is conserved. What do I mean by that? I mean, if an outcome is delayed, it can't be undelayed. Short of actually building a time machine, once that time has passed, it's always passed and we can't recover it. Likewise, if we get an exception or a failure, we can't unaccept it or unfail it. We can mitigate it, we can propagate it, as we've talked about before, but we can't cause that to unhappen. So delta Q is, once there is delta Q, then the delta Q stays and we can't destroy it. There are opportunities to trade it. So for example, we might, in some circumstances, accept more delay in delivering an outcome in return for more certainty of completion. And indeed, we'll look at an example of that as we go through our worked example in a moment. And delta Q can be represented using something called an improper random variable. So an improper random variable is one whose total probability mass may be less than 1. So that essentially combines continuous and discrete probabilities. So we have a distribution, and then we have what's called the intangible mass, the difference from a complete probability of 1, which is then what we're using that is to model the probability of exceptions and failures. So using this representation, we can encompass normal behavior and the variability in the time for that normal behavior to occur, and the possibility of exceptions and failures together in one model. And that basically makes to do straightforward, and that's important because as we've showed with our hexagonal diagram, we need to model the impact of exceptions and failures on the delivery of the performance. Otherwise, we're missing essential parts of the behavior. So, how would we go about validating performance requirements? So, one way of doing this is to decompose the performance requirement, basically following the system structure requirements, just using engineering judgment, best practice, or even just kind of cosmic constraints like the speed of light. And then we can validate that decomposition by recombining those subsystem requirements via the behavior. We'll go through an example of how we do that in a moment. But the key things about this is that's something which is formally and automatically checkable, and that can even be made part of a continuous integration process, so for regression testing and so forth. This captures the various interactions and couplings, for example, the impact of exceptions and failure behavior, and it's necessary and sufficient. So what we can say is if all the subsystems function correctly and are properly integrated, that is quite a big if, but assuming that's true, and they all meet their individual performance requirements, then the overall system will meet its overall performance requirement. So this decomposition is something which allows us to attack the overall performance problem in pieces, and we can even apply this approach hierarchically, so further decomposing our subsystems, so until either their behavior is trivially provable, for example, it's just a propagation of a signal over a piece of fiber or something, which we know exactly what the properties of that are, or we reduce this to a criteria which are either for the verification of subsystems or for the acceptance of third-party systems and services. So we're now going to work through a specific example of how this can be applied. We're going to take something very simple. We're going to look at a generic remote procedure call. It's simple, but there turns out to be enough in it to illustrate a lot of the points we want to get across. So what we're thinking about here is some kind of front end which communicates across a network to a back end. Very straightforward. So we start off from the perspective of the front end in the idle state. Then we decide we want to do something. So we construct a transaction. We send a request across the network. Hopefully the request is received at the back end. The back end processes that request. It commits the results. It transmits a response across the network, received by the front end. which completes the transaction, and we're back to the idle state. So very, very simple model of a generic remote procedure call. So when we think about the performance of this, we need to introduce some observables, some particular points at which we're going to consider the transit of this behavior. So we introduce some points here, and we give them names. And now what we're looking at is the passage times between those observable points, and those are represented by delta Q. So a little notation here is the delta Q from A to A represents the distribution of delay and the probability of failure in getting from A to B.
Sorry, Peter,
we're not going to...
That dropped out.
Okay. So delta Q there, the delta Q from A to B is the distribution of the time to complete that transition from A to B together with the probability that it doesn't succeed. Similarly for all the other parts. But the thing here about delta Q is that we can compose it. So what we're going to do now is abstract the performance. This is exactly how we said we were going to do this in a generic sense. So we're going to abstract the performance here. So we're going to say the back end is just something that delivers a function, and it does so with a certain delta Q. And then we can combine that with the performance of the network and say that from the perspective of the front end, the combination of the network and the back end is just something that delivers a delta Q. And then we can combine that with the performance of the front end and say that from the perspective of the user, this is something which delivers a delta Q. So the delta Q to go from deciding we want to do something to that being completed is the performance of the system. So what we're doing here is basically rolling up the subsystems in such a way that we get the performance of the whole system starting from a particular point. So what's the performance requirement here? So this is one that we're just making up really for the purposes of this example. So the performance requirement is technically speaking a bound on that final delta Q, the delta Q from A all the way around the loop back to F. And we're going to say that we want half the time that should happen within 500 milliseconds, with a 95% chance it should happen within 700 milliseconds and so forth. So we're going to represent that as a CDF. So that's now captured what is our quantitative intent, that's our requirement. And then we're going to decompose this A to F as the combination of what the front end does, the A to B, with what the network does, plus what the server does, and so forth. And the way those terms combine depends on the behavior. So now we need to look at the interaction of performance and behavior. Okay, so let's look at the behavior of the front end. So we're communicating across a network. We understand that there's some chance of things being lost by the network. So either the request or the response might be lost. So to mitigate that, this process does a retry. And we're saying here for this example, it'll retry after a third of a second. So that's our mitigation of failure. At the same time, we don't necessarily want to just go around that retry loop indefinitely. So after 3 attempts, the transaction is deemed to have failed, and we're propagating the failure back to the higher level. So that could, if we're trying to load a web page or something, that would come back and give us a 404 error. So we have obviously a diagram here with some loops. We've got the normal process where we construct the transaction, send the request, wait for the response, get the response, complete the transaction, and we're back. So that's the normal loop. But we also have the possibility that having sent the request, before a response comes back, we time out. So we then loop back to constructing the transaction, and we could go through that, run that loop a couple of times. So in order to get a clearer picture and to see how the method proceeds, we're going to unroll that loop. So here's exactly the same thing unrolled. So there are now no loops. We simply have paths that we can take through this set of states. So the simple path, which goes through waiting for the response, completing the transaction, coming back to the top, is the one there in green, and that path then has a delta Q, a lot of which will be dependent on the delta Q of waiting for the response, which is where we've rolled up everything to do with the network and the back end. Now, depending on that delta Q, if that's too large, so the delta Q gives us the probability that that will be too large, we may take the red arrow and time out, in which case we could follow the blue path. And similarly, we have some more paths we could take through this. So basically, we have each of these paths has a delta Q, and we then need to combine those delta Qs. So technically, this is a non-preemptive first-to-finish synchronization. Basically, we look at what comes first, but we have the possibility that a request we sent earlier, the response might come back later, and we'll accept that. And which execution path then is taken as a probabilistic choice, which is a function of the delta Q of the rest of the system. So what we do is combine the delta Qs of the different paths with those probabilities. So to run through this example, we're going to make some further assumptions. So we're assuming here that this is an application with a customer in the UK who's connected over UK broadband, and the back end is a server running in a data center somewhere in the US East Coast. So in terms of the delta Q of the network, so that's the delta Q from B to C or from D to E. We have those observation points. This is something with a minimum delay of 95 milliseconds. This is the kind of thing we measure, so we can say this with a fair degree of confidence. A variability of something like 50 milliseconds and a 1 to 2% chance of loss. So that basically characterizes the delta Qs of those portions of the process. And for the response of the back end, we're going to assume that that's basically just a distribution between 25 and 60 milliseconds. Again, these are all assumptions that we could vary, but for the sake of constructing the example, we'll start from that. So, displaying that as a CDF, the server response now is the line that you can see. So that's the delta Q from C to D. So that's from the receipt of the request all the way around through that loop to the transmission of the response. So if we combine that with the network delta Q that we just described, what we get is an overall delta Q from B all the way around to E. So this is from the front end sending the request all the way around to receiving the response that looks like this. So that's shifted to the right because we have more delay, and there's some space at the top, which is basically the possibility. We had a 1 to 2% chance of loss in each direction, and that all appears there. So given that delta Q from B to E, that's the thing that appeared in our unrolled behavior diagram from the front end. So we can add all that up, and we now get a delta Q from A to F for the whole system. So here it is, and we've plotted it against the performance requirement, And we can immediately see that this is a system which is meeting its performance requirement. So because the delivered curve is to the left and above of the required curve, there's no point at which the probability of delay of a particular delay is worse than it should have been. So we're meeting that requirement. So far the verification task seems pretty straightforward. We're basically saying provided the network and the server performance are within those bounds, our initial sets of estimates, then the front end will deliver the required end user experience. Actually, we haven't at this point incorporated any delta queues associated with the operation of the front end. We could do that. We could consider that the front end might be encrypting its transaction. That might consume some CPU resource. That CPU resource might be on a shared machine like a laptop. So all of those things could be rolled into the same analysis. We haven't done that in this case, but it would be perfectly straightforward. So given at this point an ideal performance from the front end, we can say the system will deliver the required end user experience. We've also seen that there's a reasonable slack between the delivered performance and the requirement. So we could ask the question, could we equally validate a different set of requirements? How far could we relax them? So having built this model, we have then the opportunity to explore the impact of varying the network performance or of varying the server performance. And for example, that might vary as a result of load. So now we're getting to investigating the scaling behavior. So let's have a look first at varying the network performance. So the curve on the left here is the server response, exactly the same as before. The second curve is the network performance that we had before, and the third one now is the revised network performance, which is worse. It's worse in a way that would correspond to, for example, having the back end located in the US West Coast rather than the US East Coast, or equally leaving the server where it is, but having the customer in the UK connecting over 3G rather than fixed broadband. So we can repeat the analysis, push that revised delta Q through the front-end behavior and say, okay, what does that do to the delivered performance? So what it does is this. So we can see, as you might expect, we're getting more delays. We're now sometimes not meeting the requirement. We're actually, the black curve is intersecting with the blue one, and that represents now a performance hazard. So this is not meeting its requirement all the time. So equally, we could think about the server. Let's talk a moment about the resource consumption. There's various bits of resources here that we could look at. We'll focus, excuse me, we'll focus on the resources in the server. So if we assume that this is a virtual server operating in some cloud data center, that will have some limit on the rate at which it can do I/O operations. And that's necessary so that the underlying shared infrastructure can be shared between different users of that cloud service. And as a cloud service, how much we pay depends on how tight those restrictions are. So these parameters affect the operational expenditure of running that server. And typically, I/O accesses are controlled via a token bucket shaper. So this is something which allows small bursts through but limits the long-term average use. And this represents one of these quantitative timeliness agreements. So remember, that was a relationship between applied load and delivered performance. those kind of agreements can have some structure. So it could be, in this case, we're going to say, provided that the burst load is within the capacity of this token bucket, then the delivered performance will be this. If the burst load exceeds that limit, then the performance will be something lower. That's effectively the deal that you're getting from the cloud services provider. So what this means is that the delivered performance of the I/O depends on recent usage history, which is another way of saying the recent load. So that load is a function of the number of front ends accessing the service, and it also depends on the proportion of retries. Obviously, if any given front end sends the same request again, and the original request wasn't lost, but just the response hadn't got back or hadn't gone back in time, that represents additional load on the server. And that depends on the delta Q of that whole path. Remember, we looked at the unrolled behavior of the front end, and whether a timeout occurs depends on the delta Q of delivering the response. Depends on the performance of the I/O subsystem. So that is obviously now a nonlinear coupling, which could be completely modeled. For this example, we're simply considering that there's a probability that the server might take longer to respond. So we'll, just for a first cut of this analysis, we'll introduce a certain probability that the server response might be significantly longer than the 25 to 60 milliseconds that we said in the first place, as a result of the I/O token bucket shaper kicking in and causing the commit stage of the whole process to take longer. So now we have several different curves for the delta Q of the server. So the one on the far left is the one we had before. That's when we're always having a fast response. There's no probability of taking the slow path. The next one represents a 25% chance of hitting that slow path, 50%, 75%, and 100%. So the last curve is the responses are all slow. So when we combine those with the network performance, we get a corresponding series of curves here. So that's our revised delta Q of B all the way around to E. And when we push that through the behavior of the front end, we similarly get a series of response curves. And we see some interesting kind of stepped behavior here. And really that corresponds to the server delay causing the front end to time out and send a retry. So the steps correspond to a number of retries taking place. And we can see that once again we're arming a performance hazard here, and in the case where the server's very slow, we're arming it pretty much all the time. So that will be something we need to be careful of. So if we just go back to our hexagon diagram here, we can see that we've examined the impact of the retry behavior on the delivered delta Q. So we've looked at the effect of the exception failure mitigation on the performance. We've also looked not in detail, but at least implicitly, of the impact of the retry behavior on the load on the server. And we've looked at the effect of the server loading on the delivered delta Q. So we've also been looking at the effect of scaling in terms of load on the delivery of the individual end user experience. We've also considered then the system impact of scaling. So without going into all the details of this, as load increases, we increase the possibility that the IO limit will be applied and the server will take the slow path. So we've looked at how the server IO constraint could get triggered by load. And in terms of variability and correlation, we've looked at some self-induced correlation that could be caused by the coupling of the retries due to load and its connection with the delay in the response. So while we haven't covered everything here, we've encompassed a reasonable survey of the whole space that we said needed to be dealt with in the first webinar. So just take those off. Right. So that's our very high-level discussion of the method and a quick run through a worked example. Hopefully that's giving you some kind of feel for what we're talking about here when we say, you know, we have an approach, there's a method, and some thoughts about how that might apply in your own kind of market sector or application domain. Just say a little bit about how this relates to general challenges in ICT and in particular virtualization. So virtualization, as we've been discussing, creates new performance hazards in the digital supply chain, and in particular by causing aspects of the performance of virtual servers and so forth to be out of your direct control and under the control of the, for example, a cloud provider. Some opportunities that might have been to mitigate some performance hazards are no longer available. So it changes the landscape. It also creates delta Q. It's inevitable that a virtual server will take a little bit longer to respond than a physical one. There's always it, so that creates just a little bit more deviation from the ideal of instantaneous and perfect. So it creates delta Q, and it can create quite a lot as we work through our example. As we said, delta Q can be traded, and so the question here is now, who gets to do those trades? Is it you as the user of a virtual server, or is it the cloud structure operator who trades off one user against another and thereby gets more value out of their investment in infrastructure? It also creates a need to consider ongoing resource costs, because some things that were previously in sunk CapEx now become OpEx. We talked a bit about I/O performance. Another parameter associated with cloud services is the amount of memory that they have. So whereas if we actually went out and bought a server, we would have a certain amount of memory in it. And thereafter, if we used 25% or 75% of that memory, would make no difference. On the other hand, if we're buying a virtual server, then buying one with 3 times as much memory will cost us more money. Previously, things we didn't worry about become a cost issue. And we also need to consider opportunity costs. So because virtual instances are shared between multiple users, executing one person's server necessarily takes away the opportunity to execute someone else's, and this can be seen in the way, for example, Amazon Web Service price their compute instances and various other services that the industry as a whole is needing to grapple with. So thinking about this more generally across ICT, the first requirement is the need to establish a quantitative intent. And while it may be difficult to get definitive statements about what's required. It may be possible to get some agreement on what really isn't acceptable. So, excuse me. While the marketing department may be reluctant to say how long it should take to load a web page, they may agree that taking 30 seconds is definitely really too long, which gives them something to work on. Another way of getting these quantitative intents is a comparison with something else. So it must be better than it is at the moment, or it must be better than this competing product, or something of that kind. That could then be measured, and that would provide then a baseline for what the intent is. Vague statements like the best possible or whatever will sell really aren't any kind of quantitative intent, nothing that you can then do any sort of engineering with. But given some quantitative intent, what you can then do quite easily is just to approximate the best possible delta Q. So you can simply take the minimum possible times things might take and add those up. If you want to be a bit more sophisticated, you could take means or even variances, and those just add up. So there's no particularly complex analysis needed there. That creates a quick check on feasibility. If it doesn't work, if it's not going to work when you just take the minimum times things could take, it's not going to work under any circumstances. Adding means, taking into account means, is it going to work on average? Taking into account variances will say, start to give you some estimate of the chances of failure and so forth. This also puts some bounds on the scope for future improvement. So having said this is the best possible, whatever we do is going to be worse than that, and we're never going to be able to do better. Excuse me. And it provides some early visibility of where the performance hazards may occur. So you can see the places where the delivered curve is getting a bit dangerously close to the requirement. That gives an opportunity to say this is what we need to look out for. It may establish even some KPIs that you need to measure and give you the opportunity to put mitigation in early before performance hazards mature and anyone has a problem. Okay, so to summarize, system performance validation consists of analyzing the interaction of system behavior and subsystem performance requirements to show that this meets the quantified user requirements, the QTA. Verification consists of showing that subsystems meet their QTAs, which we can do either by analysis or by measurement of the delta Q of their observable behavior. So that then provides a set of acceptance and/or contractual criteria for the third-party subsystems and services that you use. And if you can impose those, then you're substantially reducing the performance risks of the integration and hence the costs of rework is an issue for quite a number of you in our focus group. Okay, so we're getting towards the end of this webinar. What next? So here are some questions. So the interesting thing is, given the right inputs, this sort of analysis actually takes relatively little time and effort. So the example that I showed you took us less than a day to work through, and all the graphs that I've shown you in this presentation were generated in less than a second of processing time on a laptop. So it's not computationally intensive. This is much cheaper to do than masses of discrete event simulations and so forth. However, having the quantitative intent is fundamental. Found. Other questions are which parts of the system decomposition are forced and which are under your control. So if you have to use some existing infrastructure such as a network, then that's something that needs to be factored into the analysis. Characteristics may be completely undocumented. So one way of dealing with this is to push the verification process into real time. So to do in-life measurement of the delta Q, which is driven by the requirements coming from the validation, and that then gives something that can be used operationally to be forewarned of the possibility of performance hazards. And this actually doesn't need to be expensive because this is a very focused approach. The amount of data that needs to be analyzed is quite small. This has nothing to do with big data. This is really looking at those parameters which are directly operationally relevant. So our ask, as we said at the beginning, is for you to think about where and how such techniques could be applied in your own organization or industry sector. What would be, considering the sort of process that we've looked at, obviously that needs to be wrapped in some way into some sort of tools or services, what would the constraints on those be? And how could the value of doing this, of managing these performance hazards, be made relevant to your situation? How could the benefits be quantified? Like what would the benefits be? Is it a reduced time to market? Excuse me. Would it be a reduction in the risk of contractual penalties, or would it be the ability to address new markets where it might require safety cases and so forth? What would that benefit be? So we're going to be asking this group for volunteers to engage in a 1 to 2 hour telephone interview discussing these points, and the results, obviously anonymized, will be fed back in the final webinar that we'll say a bit more about in a moment. So thank you. Are there any questions come through? Hand over to my colleagues who hopefully will be monitoring that.
We've not actually had any questions that have been answered as we've been going along. So if you can think of any, please feel free to put some in right now. And thank you all for coming.
So obviously we still have the opportunity. You can use our general PEnDAR email address to ask any further questions which come up later. This will occur when if you review this webinar from the recording. Otherwise, I think if there's no questions, I shall hand back to Christian.
Thank you so much, Peter, and thank you so much to our support team here at Neil and to Lucy, and most of all, thank you to all of you that logged into the session today to take part, to submit your questions. The recording of the session will be emailed out tomorrow, so you can review that if needed. If you do have any other questions, now is your last chance to put them into the questions panel and submit them. We'll keep the room open for about another minute, and then I will close the room down. But otherwise, really appreciate your attention and your contributions today. The third webinar registration link has been put into the chat box there, so please do click on that and register for it now. That will be on Thursday the 18th of May at 4 p.m. UK time. So please do register for that third and final webinar now. And otherwise, it looks like that's it for questions. So thank you so much, ladies and gentlemen. I'm going to end the broadcast now, and we look forward to seeing you in the third webinar on the 18th of May. Thank you very much, and goodbye.